CLI and a cross-platform IDE for C and C++. Download now.
Hi all, thank you for joining my session and welcome to my session. So we the developers, right? So we encountered a couple of bugs, a couple of category of bugs in our everyday coding life, right? That can be a logical bug, that can be any kind of bugs, right? Out of which the most irritating one I would say is a concurrency bugs. So today let me introduce a tool or remind you about a tool that can help you to detect that concurrency bug much earlier than it went to the production. So we'll go directly into the presentation. So this is not the tool, this is me. So yeah, a quick glimpse about me. I'll share the slide later so you can have at that time also. So yeah, going forward. So as I told before, considering the other bugs, right, logical bugs, the syntactical errors, that kind of stuff, why we need to care more about concurrency bugs? What is so special about these bugs, right? So the first one is very hard to detect because the logical bugs, if you take an example of logical bugs, we know from we somehow know from where it can produce, right? Because it's me who created the bugs, right? But for concurrency bugs which will create from a legacy code or something, it's very hard to detect because we don't know what is the exact cause of the bugs, whether it is a data race, a mutex violation, or whatever it is, we don't know. That's the first thing about the concurrency bugs, very hard to detect. That's why, because why I am saying about why we need a tool for helping us to detect the concurrency bugs. The first thing is this hard to detect, and the next one is the impact. The impact is too severe. Maybe it will be a small one, or it can be catastrophic as well because it can lead to unpredictable crashes, data corruption, and critical performance degradation as well. And when it went costly in production, because it went to into production, somehow it went to production because the chances are higher. So it went to production. It can damage your reputation. It can damage your time as well by providing cost significant patches altogether. So I'll just go through some examples of concurrency bugs which encountered in the world and made some hiccups. So you may heard about Linux kernel privilege escalation or the dirty cow exploit, where a race condition in the Linux kernel copy on write happened, and this caused underprivileged user or unprivileged users right to read-only memory. So this is a crucial bug, and it is the root cause is a small improper synchronization between memory check and write, and they provide emergency patches to fix that thing. And second thing happened, the Google Chrome's animation component, where a race condition in the animation component enabled arbitrary code execution, and this exploited in zero-day attacks, and it was so critical, allowing remote code execution. And the third one, as you saw about this, you already understood about what is the criticality of this concurrency bugs. This happened in the flight control software of Boeing 787 in Dreamliner, where the continuous operation of 248 days could lead to catastrophic failure of the software, and you know what will happen next, right? Yeah. So as I said previously, also the concurrency bugs which can cause the impact is catastrophic, right? It can cause catastrophic issues. So who is helping? Who is helping? Who can help to can detect this concurrency bugs much earlier? It went to the production. So yeah, that's a Threadsanitizer, which is a hero of this presentation or the session. It's a dynamic analysis tool for detecting data races and all other synchronization issues. And it is integrated into popular compilers like LLVM and Clang and GCC as well. But unfortunately, MSVC doesn't have the support due to some technical issues like code instrumentation and all. It's work by code instrumentation, which we will explain it later in the slide. And using the instrumentation code instrumenting thing and setting the flags and all, it will provide detailed report for the developer to analyze the issue. So let's look at this, how Threadsanitizer evolved a little. So it started as a Valgrind tool in the internally and Google. Due to just very slow as a Valgrind tool, later it integrated to compilers like LLVM and Clang, and this significantly reduced its overhead, making the birth of Threadsanitizer version 2. And then it went to an open source one, and more contribution happened to that and integrated to LLVM and GCC, making it as a broader developer community. And it became a key part of the several companies adopting the registration tools, including Chromium. And later it integrated to companies like Google, Facebook, and used TSan for testing and extended its availability across various operating systems as well. And then in the modern era, it's continuing its support. And it's actually it's helping for C++ as well as Go as well. And integration with fuzzing techniques like libfuzzer is very crucial for uncovering race conditions like the mutex violations in the automatic CI/CD pipelines. So which are the common bugs which can be detected by the TSan or Threadsanitizer? First of all, the data races. Data is like unsynchronized access to shared variables which can lead to unpredictable behavior. It can detect that. And the mutex issues like the uninitialized one, unlocking and the proper unlocking or proper improper locking of the mutex that can detect. And the lock ordering as well. For example, if I locked it correctly or not, or if I locked it, then I didn't unlocked it properly, and then again I double locked it. That kind of stuff it can detect easily. And use after free. It detects memory corruption issues. Oh, sorry, it can do that. There is a misconception in the sanitizer family that this will detect this memory issues as well. No, it can't, because it is the threat sanitizer is mainly used for concurrency bugs like data races, mutex issues, and lock ordering. For memory thing, we have address sanitizer and other sanitizer for that. So this misconception have to be changed. So when we say about sanitizer, people will think like it can detect everything. It can't. For each purpose, we have different sanitizers. This is a sample code for the with the race condition where there is a counter increment. This is kind of considered as a benign race, but I'm just providing an example for this counter variable increased. So there is a chance for the race condition in this code. So when I say about when I say yeah, thread sanitizer can do that, thread sanitizer can do this, you people may not believe. Like, so I have some evidence here. So it have to be live session, but due to some hiccups in my laptop, I had recorded that the code which can provide which can detect the data race and how it is detecting, how it is creating the summary and all. So yeah, it's an example of this code is here. So yeah, in the insert or update function, there's a chance of a data race. So there is a writer and reader thread as well, 2 writer threads and 1 reader thread. So that's about the code. And when you try with the thread sanitizer and provide the thing, yeah, this is the summary. It generates, there's a very detailed report, and for the lazy people, it generates a summary as well. Like what happened with the code, where it is actually creating the problem and all. Yes, so that's a one example. This is second one. So here what I'm showing is like we can annotate TSan that we can make TSan think like there is no problem by TSan annotations. So here there is a this code actually create a problem. The writer thread is actually creating some issues, but I kind of annotate it, and there will be no detection by TSan. Yeah, simply this code will execute without any problem. So that's it. And going forward, there's another thing where we use an external library function. And this I will, this why I showed this code is like to emphasize you about the importance of code instrumentation here. So this is a library function outside the our code. We deliberately will not instrument that particular function, right? Sorry, the file, and we run it. We just instrument the other file only. So here also we can see, yeah, done. There is no problem with this file also, but actually there is an issue. But we kind of make TSan think that there is no problem. So one of the main advantage of TSan is the seamless integration. So as you already saw in that code, right? The just adding this compilation flag make the code instrumentation happening in that particular file, and it will sanitize this particular function as a file. So the particular workflow will be run your test using TSan and analyze the report and incorporate TSan run into your continuous integration pipeline for early detection of concurrency issues. So going forward, we check about how Threadsanitizer works. So here compiler have a big clap for compiler where it will help actually to TSan to solve this concurrency bug detection. So the compiler will insert hooks in all the memory read and write operation, and it add runtime calls for TSan aware function to convert the our memory read and write operation to TSan aware functions. So TSan let TSan know that yeah, there is memory read and write operation. For example, the x equal to 42, there's a write operation, right? So compiler might emit a hook there and convert into TSan write it as a TSan aware function. And it's wrap the synchronization primitive as well. For example, mutex, atomics, or replace the TSan aware functions. And it actually manages shadow memory for the overall copying or what you can say, the understand the thread context, address, size, etc. It manages shadow memory for its operation, and it tracks the happens before thing. So I will explain in the next slide what is the happens before thing between two threads. And based on this happens before relationship, TSan detect that the concurrency or data races issues. So happens before tracking. What is happens before rule? So I will give you an example that, for example, thread A and thread B are doing a relay race, and thread A is having the baton with them. And if thread A give that baton to thread B know about thread A in all manner. Like for example, thread B know all the things what thread A had done before. But what if thread A is a little bit greedy and it didn't provide the baton to the thread B? So there is a chance of potential data risk. Thread B doesn't know about anything about thread A, and there is a chance of happens before violation, and there is a chance of potential data risk there. So yeah, that's and how TSan knows these things. First thing is vector clock basics. Here, the vector clock is the main thing about the how this happens before thing is working and all. So here each thread made a vector clock, which is an array of logical timestamp. It represents what the current thread knows about the progress of other threads. If, for example, I have two threads A and B. So thread A contains two indices, 0 and 0, where 0 first index marks for the timestamp or the information about that thread itself, and second index will be for the next thread. So that's the vector clock thing, and when there is a mutex locking and unlocking, there is a merging of this vector clock will happen, and it happens before tracking will happen. Yeah, as I said, this clock merging happens. So let's think about this code as an example. So here A releases, A have this vector clock of 20 because A actually have a mutex, it's have a write operation already. B have a vector clock of 00. So when A releases the lock, this vector, that particular mutex have copied the A's vector clock, that is 20. And B acquires the lock. During that acquisition, there is a vector clock merging happening, and B will get the value of 20. And as B got acquires a lock L, it increment the timestamp to 1 and B become 2-1. And then TSan will compare these two vector clocks. That is, one is A have 20 and B have 2-1. And A less than or equal to B, that is, there is happens before relationship between A and B, and thus there is no potential data race. There is no potential data race. But what happened if B didn't acquire the lock? If B becomes 0-0 and A become 2-0, and B will increment its local time to 0-1, and then there is a problem, right? So there is a potential data race. That's how TSan detect the data races. So that's the best practices with TSan. So test your code, always test code with TSan. Understand its full potentiality, use its full potential to understand, to test your code, find the hidden concurrency bugs, and combine all the sanitizer. As I told, this address sanitizer is there to detect the memory issues, and undefined behavior sanitizer is for the undefined behaviors. So use a comprehensive error detection, use Threadsanitizer along with the address sanitizer and undefined behavior. And annotate the benign races. Use TSan suppression techniques to annotate the unwanted data races. For example, some data races may be deliberate, right? So that can be annotated. And always use TSan in a dedicated environment, not in a separate production or simulated environment, because TSan is a little bit slow. That is one limitation of the TSan. So use TSan in all the dedicated environments. So as everybody does, TSan also have limitations. So that is one is performance overhead. As I already told, it slow down your process to 3x to 5x. And it always have a build requirement, because we already saw that code instrumentation is very much for TSan. So it requires instrumented builds. It cannot be used directly on uninstrumented production binaries. And primarily target data races and synchronization errors. It does not directly catch logical bugs or deadlock, because it's not a limitation, but I simply added that because it doesn't have the capability to detect your logical bugs or deadlocks. And sometimes can false negative as well. Sometimes that's because it's powerful, but it misses some complex concurrency issues in sometimes because of some shadow memory issues or something like that. We don't yet don't know why it's producing the false negatives, and work is going on to solve that thing. So yeah, the key takeaways is TSan is essential. So you need to use Threadsanitizer to find the hidden concurrency bugs, and integrate early to your production environment, integrate early to your CI/CD pipelines to catch these concurrency bugs before it went to the production. And avoid production headache. As I told, avoid production headaches. Don't wait for elusive concurrency bugs to emerge in the production. Catch them when they are cheapest to fix. And then continuous improvement. So regular use of TSan for robust, predictable, and high performance multi-threaded application. Using TSan will improve your code, improve your concurrency bugs lifetime as well. So yeah, so we all know sanitization helped to provide much better world. In the past, we know from 2020, right? Sanitization helping people to avoid viruses and all. So here, sanitize your code as well. Sanitize it before you ship it. That's it. Thank you. So we'll gather down for any doubts and all. Yeah, that's from my side. Thank you.